Hello group members, this is Andy, and today I'm going to talk about Hplc, or High Performance Liquid Chromatography. We will go through the basic concept of chromatography first, and then I'll show you how to operate the Hplc instruments in our lab. High Performance Liquid Chromatography is a technique used by this lab to separate a mixture of peptides in order to create a pure sample. A familiar demonstration of the concept of chromatography is the separation of ink using paper and water. In comparison with Hplc, we can see some similarities between these two experiments. The black ink in this case would be our sample, and the paper is the stationary phase, or our column, and the water is the mobile phase, which will assist in moving the sample through the column. On the Hplc, we must include a UV detector so we can discern the different components of our sample. This is similar to our eyes being able to see the different parts of the ink once it is separated. For Hplc, our stationary phase includes various hydrophobic C4 and C18 reverse phase columns. We usually use C4 for large proteins and C18 for smaller peptides. For our mobile phase, we utilize the ability to make gradient mixtures of two distinct polar solvents in order to maximize the purification of our peptide. Our lab labels these solvents as solvent A and solvent B. A is 100% water and is used to equilibrate the column. Solvent B is added at an increasing rate, which can be modified specifically for each sample. In most cases, we use 90% to 10% ratio of acetonitrile to water for solvent B. 0.1% of TFA is added to both solvent A and B before the run occurs. We do this because of the following reasons. TFA as an ion pairing agent alters the retention of the sample in the column and allows for peptides that usually coalute to resolve separately, meaning a better separation and sharper peaks. Another reason is consistency. We must make sure that the concentration of TFA stays consistent between runs, or else the target peak might elute at a different time. First, we must make sure that everything is in order before we run our sample. Check to see that the waste is not near full. Make sure that there is enough solvent A and B for the amount of runs you need. That way, the lab can always have Hplc solvents available for use. Create the sample that you want to run. The concentration and amount of your sample depends on what column you are using. We usually add near the minimum amount that the column can handle because it gives better resolution in the chromatogram. The three sizes shown here are prep, semi-prep, and analytical. For the prep column, the largest column, we add 5 to 10 milligrams of peptide each run. For the semi-prep, it goes down to about 1 milligram. And lastly, for the analytical, 0.1 milligrams of peptide is the recommended amount. These amounts are based off of a 2 to 3 kilodalton peptide sample. Make sure your sample is fully dissolved for it to be effectively separated by the column. To switch to a desired column, unscrew the plastic screws on the top and bottom of the column attached. Then simply attach those screws onto the desired column. The sample loop can also be switched out to the desired volume. In this case, the 1 ml sample loop is attached and can be changed out by unscrewing the plastic screws on either side. With everything in order, we can now inject our sample. We must first open the Unicorn program and open up the system control window. There, go to the top and select Manual, then go down to Flow Path. By default, the parameter selected is Injection Valve. Modify the position parameter from Load to Inject, then hit Execute. Once executed, we can pull out the needle by unscrewing the metal cap. Now we can take up our sample. For this example, we used a 1 ml sample loop, and therefore a 1 ml syringe. If there are air bubbles in the syringe, we must flip the syringe and squeeze the bubbles out in order to prevent gas from entering the column. Let's see that in slow motion. We can now replace the syringe back into the instrument. Do not over-tighten the metal screw cap, as the plastic tip on the cap may deform, causing poor injection. Once the needle is attached, we can change the parameter back to low. Make sure to click once or even multiple times on the execute button to ensure you have an airtight seal between the needle and the injection valve. Then we can inject our sample. Now we can start our run. Click Run. We are greeted with the Run window, which consists of a list of methods we can use. Make sure the method at least matches the scale of your run, whether it is prep, semi-prep, or analytical. After highlighting the desired method, hit OK. The next window shows variables that one can change about the run being done. One variable to take note of is in the sample injection block. It's called empty loop width. This value in milliliters depends on the size of the sample loop mentioned earlier. It simply washes the sample loop with the inputted amount. We usually want twice the volume of the sample loop, and sometimes even a little bit more for bigger sample loop volumes. This is to ensure that the sample is completely washed out of the sample loop and transferred into the column. Clicking next 2 more times shows us the gradient window. This simply displays what sort of gradient the selected method runs, with percent solvent B on the y-axis. In this case, a linearly increasing gradient is used, but other gradients can be created with different slopes of increasing solvent B to take advantage of a known elution time of a specific peak. Clicking next 2 more times shows the result name window. This is where we can name our result file appropriately, as well as control where this file is saved. Clicking Start initializes the run. Now we wait to collect our peaks. While the run is going, we have some extra options in the top left corner. We can press the hold button to hold the gradient of percent solvent B at its current percentage. We can also pause the run by pressing the pause button for the times when your run just has to wait until you have time to tend to it. There is also the end button, which ends the run. It will ask if you want to save a partial result. The result, along with all other runs, can be analyzed in the evaluation window. Now we're nearing the part of the run where our sample elutes and we want to collect the peak. Make sure there are enough test tubes for the amount of fractions that you are going to collect. We click on Manual, then Frac to pop up the fractionation window. Choose Fractionation 900. Type into the message box the amount of milliliters to collect before the fraction collector changes tubes. This is how the fraction collector operates. After inputting a number into the message box and pressing Enter or Execute, the fraction collector will attempt to collect that volume of sample. Hitting Enter again while there is a number in the message box will signal the fraction collector to switch to the next test tube. Inserting a 0 in the message box will stop collection and reroute the elutant back into the waste. However, the fraction collector will change test tube. It just won't output any elutant into the test tube. Until, of course, you insert a positive number back into the message box, in which the fraction collector will start collecting again into the current test tube. All that information seems a little confusing, so let's try to apply what we know about the fraction collector to analyze the chromatograms that have already been done. We can understand how the fraction collector works a little better if we check out one of the chromatograms that's already been done. Looking at the x-axis there, we see that there's 3 fractions that were collected. And how I know this is because of the marks for 1, 2, and 3 there, with a waste in the middle. So how that was accomplished manually through the fraction collector is when the first peak was starting to come out, we would type 10 or a positive number into the message box and hit execute. And then once that peak was finishing, we typed in 0 and pressed execute, changing it to the waste. And so the rest of those peaks are now going to the waste until we saw another big peak come out, which is the second peak. We inserted a 10 again and pressed execute, and so the second fraction was being collected. Then we realized that the second peak actually had another component, so we had to hit execute again with 10 still in it in order for the fraction collector to quickly switch from 2 to 3, the third test tube. And finally, when the third peak With finished, we hit 0 and press execute, and the rest is waste. In the evaluation window on the left side, we can see a list of all the previous runs listed by name. We can double click a name to open that run. We can then analyze the chromatogram and the quality of our fractions using a left click drag function to zoom into specific areas of the chromatogram. Zooming in further, we can see exactly where our fraction collector started and switched collection in a specific test tube. Right-clicking and choosing marker makes a marker appear showing you the intensity of the peak at any point the marker lies on. Left-clicking the other line components, such as the lime-colored %B line, now changes the marker into a lime color and will show you the % solvent B of any position on a peak. This tells you at what %B a peak elutes, which is useful for future runs of this specific sample. Right-click and reset zoom resets the zoom, or undo zoom if you want to undo the previous zoom, but not reset the whole thing. This nifty zoom function and the marker are also available in the system control window, so you can actually look at the peaks close up while they're eluting, as well as analyze what %B they're eluting. Thank you for watching this HPLC tutorial. If you have any other questions, you can ask any group member and they'll be happy to help.